So flip over to the front. That first group there are what we call our even and odd identities. What I was wanting you to see is that sine of a positive angle is the opposite of the sine of a negative angle. Okay, that is a characteristic of an odd function. When you plug negative x into the function, it's the exact same answer as when you plug positive x in, except the sign is the opposite. Okay, so sine of negative theta is equal to the negative sine of positive theta. How this is helpful, if you're asked what is the sine of negative 3 pi over 4, and the whole negative angle thing is just throwing you for a loop, then you can find the sine of positive 3 pi over 4, which would be what? Positive square root of 2 over 2. And then you just change the sign. So it would be negative square root of 3 over 2. Square root of 2 over 2, excuse me. Okay? Cosine, on the other hand, is an even function. Even functions, when you plug in negative x, you get the same thing if you plug in positive x. Remember, it's that symmetry across the x-axis. So f of negative 2 has the exact same value as f of positive 2. The same thing happens with cosine. The cosine of negative 3 pi over 4 is the exact same thing as the cosine of positive 3 pi over 4. Both of them are negative square root of 2 over 2. Tangent is also an odd function, okay? And it kind of makes sense because tangent is a combination of sine and cosine. So if one of them is negative and one of them is positive, then tangent would be negative, or just the opposite. So tangent is an odd function. So those are the even and odd function identities. The next block that I wanted you to do was showing you, now it's not enough for a proof, okay? Proofs, just because you come up with several examples of something being true, does not guarantee that it's always true, but in this case, we're just kind of shortcutting it. But it does turn out that it is always true. Okay, sine squared plus cosine squared. It does not matter what theta is, as long as it's the same angle for both. When you plug it in and square the answer and add it to plugging it into cosine and squaring the answer, you're always going to get 1. And then I'm going to show you kind of where the others come from, their derivations of sine squared plus cosine squared equals 1. I'll show you here in a minute. Excuse me, but where they come from on your worksheet, I asked you to do cosecant squared minus cotangent squared. That always equals 1. So at the bottom, I had it. I had 1 plus cotangent squared. That is equal to cosecant squared if you rearrange that equation. Same thing with the secant squared and the tangent squared. Okay. So that's what you should have at the bottom of those. Now, on the back, some of you got there, some of you did not get there. I'm not all that overly concerned about it because honestly, I've seen like one occasion in calculus where they've actually asked you to use that property, but it's the sum and difference. Here's what you need to have written in that blank down at the bottom. I'll explain it here in a second, but write it down exactly that way.
Did you actually get one problem? Just go ahead and write it.
No problem. All right, so if you glance at the table really quickly, and if you do glance at the table really quickly, what I was trying to show you was that if theta is something like 75 degrees, 75 degrees is not on our unit circle. Now, we have a graphing calculator that will just spit out the value of the cosine of 75 degrees if we plug it in. Where this came from was years ago, before they had graphing calculators, they would just tell them what the value of cosine of 75 degrees was. All they had was the unit circle, because 75 is the sum of 30 and 45, and they said, well, we know the value of cosine of 45, we know the value of cosine of 30, somebody much smarter than me figured out that this relationship exists. If we multiply the two cosines together, we multiply the two sines together, and we subtract them, this answer right here in radical form will be the exact same thing as the decimal version that you get from your calculator. Now, here's the deal. With the cosine one, you've probably never seen it as a negative over a positive. You've always seen it plus or minus, not minus or plus. It does matter. When you are adding two angles, you're going to subtract these two values. When you are subtracting two angles, you're going to add these two values right here. Okay? Now, that one's just true with the cosine. For the sine, I've got it written on there already for you. Both of those are plus and minus. So when you're adding two angles, you add those sums or those products. When you're subtracting two angles, you will subtract those two products to use that identity. These are what we call our sum and difference identities. Again, I don't see them testing you on it, but I did want to show it to you in case somewhere down the road in the future you do see it again. At least I've shown it to you. Okay. So what we're going to focus on are what we call the Pythagorean identities. Okay. So here is the focus for today. So we need to take a few notes because then I'm going to show you how we're going to prove some identities. And this is like my favorite thing in Trig to do because I love puzzles and it's like a big puzzle pretty much. All right, so the Pythagorean identities. This is why, oh yeah, she's over there. Okay, this is why sine squared plus cosine squared always equals 1. If we're thinking about the unit circle here, the radius of the unit circle is 1. So I'm going to label that hypotenuse with length 1. The horizontal value right here is like your x value. Okay, it's like your x value. So that's the cosine of theta because our x value on the unit circle is equal to the cosine of the angle. And the vertical side here is the y value. So that is equal to the sine of theta. Well, this is a right triangle. Any right triangle we can apply the Pythagorean theorem to. So if we square both legs, add them together, it's equal to the hypotenuse squared. That's where the Pythagorean identity, sine squared plus cosine squared equals 1, comes into play. It doesn't matter what angle you're talking about. Pi over 6, pi over 4, pi over 3, 10 degrees, 80 degrees. It doesn't matter what theta is. When you add the sine of the angle squared plus the cosine of the angle squared, it's always going to equal 1. Now, here's something I've got written up there in the corner. There's a distinguishment with where you put the exponent. Okay? So when we want to square the entire value sine of theta, the squared goes between the trig function and the angle. Okay, we read it as sine squared of theta, but really what we're doing there is we are taking the value of sine of theta and we are squaring it. Okay, you plug in the angle and then you square that number. So sine squared of pi over 6, sine of pi over 6 is 1/2, 1/2 squared is 1/4. Okay, the right side of this equation with no parentheses, with the squared where it's at, what's happening here is you're squaring the angle. Okay, you are squaring the angle. So you would square pi over 6, get pi squared over 36, and then plug that into sine. It's not going to be the same answer. Okay, there's a distinct difference between those two right there. Excuse me. Okay, so it's very important where you put the squared. And here's the other thing. Trig functions mean nothing without a variable. Okay, you cannot just write this right here. That means nothing. Okay, that literally means nothing because sine is a function. A function has to have something plugged into it. Okay, so don't get lazy. Don't get in the habit of not writing a theta or an x or something. Okay, it's got to have an angle. or it doesn't mean anything. That is not acceptable right there. Okay, so sine squared plus cosine squared equals 1 is the most important one. It's the most common one that you will see. But let me show you where the other ones come from. You may see it with different parts of it isolated. So cosine squared theta is equal to 1 minus sine squared of theta. Okay, if we just isolate the cosine squared by subtracting the sine squared, it's the exact same thing. We've just rearranged it. We could also isolate the sine squared. So it's 1 minus cosine squared. Okay. So let me show you where the other ones come from. If we go through, we start with sine squared plus cosine squared equals 1. We know that's true. It comes from the Pythagorean theorem. If we go through here and we divide each term by sine squared of theta, which we can do, because if you do the same thing to every term in an equation, it's perfectly lawful in the laws of math, as long as you do it to everything and both sides of the equation. We're just rewriting it. We're not changing anything. We're just rewriting it. Let's simplify. Sine squared divided by sine squared is 1. Cosine over sine, what is that equal to? Cotangent. And they were both squared, so it is equal to cotangent squared. Okay? And 1 over sine squared is equal to cosecant squared. Okay? That's where our second one comes from. Okay? 1 plus cotangent squared of theta is equal to cosecant squared of theta. We can rearrange this one just like the other one. If we want cotangent squared by itself, we just subtract 1 from both sides. If we want 1 by itself, then we just subtract cotangent squared from both sides. Okay, so all three of those statements say the same thing. They're just in different arrangements based on what we need. Okay, so how do you think maybe we're going to get the third version? Divide by cosine squared. Okay, divide by cosine squared. So sine over cosine is equal to tangent, and it was squared, so that's equal to tangent squared. Cosine squared over cosine squared is 1, and 1 over cosine is secant, but it was squared, so it's secant squared of theta. So that is our third version of the Pythagorean identity. But again, it's just, it all comes from the sine squared plus cosine squared equals 1. I show you where these come from so that you don't look at it as, oh crap, I have 9 different equations that I have to memorize right here. You really don't. They all come from the first one. As long as you know sine squared plus cosine squared equals 1, you're good. And if you understand how to derive them, you can get the others. And then it's just rearranging the equations. Okay? So we can isolate the tangent squared, or we can get it equal to 1. And that is where all 9 versions of the Pythagorean identity come from. Okay, so here's how we're going to use them. This is what is called a trig identity. Okay? Cosine cubed of theta plus sine squared of theta times cosine of theta is equal to the cosine of theta. So it looks like an equation, okay? But we're not actually trying to solve for theta, okay? I repeat, we are not trying to solve for theta. What we are trying to do is we are trying to prove that all this stuff on the left side is equal to what's on the right side. Okay? Can we rewrite the stuff on the left side so that it's equal to the right side? So here's the I don't want to say there's only one rule, but there's one major rule in proving trig identities. You cannot work on both sides of the equation. You got to pick one side and you got to stick with that. You cannot move things from one side or the other. We're trying to make the left side look like the right side. So, does anybody see anything that we can do to simplify or rewrite or do anything to the left side right there? Okay, not divide by cosine, but we can factor out a cosine. Both of those terms have a cosine in them. Okay, that has cosine cubed. So we are going to factor out a cosine of theta. When we do that, we are left with cosine squared of theta plus sine squared of theta. And we need to always write that it's equal to the cosine of theta so we can keep in our minds what we're trying to get this to equal. Now, here's where our identities come into play. What is cosine squared plus sine squared equal to? 1. So we are going to replace cosine squared plus sine squared with 1. And then, of course, cosine times 1 is just cosine of theta. And I know it seems really, really redundant, but at the very end, you do need to have the line where the left side equals the right side, okay? Because it's not that this is the answer. I knew the whole time that the answer was cosine of theta, but the answer is showing how to get there, okay? All right, let's look at this one, and you're probably wondering why I went from 1 to 4. These are coming off of a worksheet. They're numbered that way. So you'll see here in a minute. All right, so we are trying to prove that the cosecant of theta divided by the secant of theta is equal to the cotangent of theta. Okay, once again, we got to pick one side or the other to work on. We can't work on both of them. So which side do you think we can do more with? The left side, okay, the left side. Now, a technique to approach these is usually we need to put things in terms of sine and cosine. Okay, we normally need to write things in terms of sine and cosine. So I'm going to replace cosecant of theta with 1 over what? What's cosecant equal to? 1 over sine. And I'm going to replace secant with 1 over cosine. Okay, what do we have? What do we do when we have a fraction divided by a fraction? We keep the top one the same. We flip and multiply. This is why we did the rational unit before we got to trig. Okay, and then what is cosine over sine equal to? Cotangent. And that's it. Okay, that's it. Okay, let's look at another one. We've got cotangent of theta over cosecant squared of theta minus 1. We're trying to prove that it's equal to tangent of theta. Okay, at this moment, I'm not going to mess with the cotangent yet. I'm not going to mess with the cotangent of theta because anytime I see a trig function squared and a 1, I'm automatically thinking Pythagorean identity. Okay, what is cosecant squared minus 1 equal to? Cotangent squared of theta. Okay, cosecant squared theta minus 1 is equal to cotangent squared of theta. So I'm going to replace it because they are equal to each other. I'm just going to put it in its spot. All right. Now, what is cotangent of theta over cotangent squared of theta equal to? 1 over cotangent. Think about it as x over x squared. Okay, x over x squared is 1 over x. So cotangent over cotangent squared is 1 over cotangent of theta. Well, isn't cotangent of theta the reciprocal of tangent? 1 over cotangent is equal to tangent. How are we feeling? Okay. I got a few more to show you. I know this is brand new. You've never done anything like this before. I get it. If I need to go back and explain some steps somewhere, let me know. Okay? But let's look at a few more first and see if we can get some more comfortable with them. Okay? Let's look at this one. Sine of theta times 1 plus cosecant of theta. We've got to see if we can make that equal sine of theta plus 1. Okay? We don't have anything squared. We can rewrite cosecant as 1 over sine, but Connor said it. What happens if we distribute the sine of theta to our parentheses here? Sine of theta times 1 is sine of theta, plus sine of theta times, how about we go ahead and write that as 1 over sine of theta. Cosecant is 1 over sine of theta. Well, what happens when you multiply something by its reciprocal? It equals 1. It can't, whoop, my equal sign's in the wrong spot here. It said equals when I wasn't ready to write it. Okay, either they cancel or you can look at it as like 2 times 1/2 is 1. But either way, 2 steps and we're there. Okay, now some of them are more complicated, but some of them really are that simple. Any questions about that one? Good with that one? Let's look at this next one. This one's fun. We've got secant of theta plus tangent of theta over cosine of theta plus cotangent of theta. And somehow we got to make adding something in the numerator and adding something in the denominator. Somehow we're going to end up with just sine theta secant squared of theta. All right. So I told you a second ago, it's usually helpful, if we don't have any Pythagorean identities, it's usually helpful to turn things into terms of sine and cosine. So let's start with that. Let's turn our secants and tangents and cotangents into sines and cosines. So secant is 1 over cosine of theta, plus tangent is sine of theta over cosine of theta. I'm going to try and say the thetas more often. Okay, cosine of theta, we're just going to leave that one as it is right now. Plus cotangent is cosine of theta over sine of theta. Okay, well that looks like I just made my problem even bigger. So what do we call that big thing right there? It has a name. A complex fraction. Okay, a complex fraction. So what do we do with complex fractions? Okay, so we can get a common denominator, or we can multiply everything by the common denominator to try and eliminate. Okay, so I don't know. I'm trying to think of which way I want to handle it. How about we just eliminate our denominators like I've always shown you, okay? Let's just eliminate our denominators like I've always shown you. So we've got cosine of theta in the denominator, and we also have a sine of theta in the denominator. So we're going to go through, multiply everything by cosine theta, sine theta. Oops. All right, so cosine cancels in the first one. So we've got sine of theta plus cosine cancels there. So sine of theta times sine of theta, sine squared of theta. Nothing happens here. So we get cosine squared of theta, sine of theta, here the signs cancel. So cosine times cosine is cosine squared. All right, it doesn't appear that we're making too much progress, but we actually are. A little bit more than we think we are. In the numerator, let's factor out a sine of theta. Okay, when we factor out a sine of theta, we've got 1 plus the sine of theta. What can we factor in the denominator? Cosine squared. Do you see where this is headed? Not yet. When we factor out the cosine squared, we get sine of theta plus 1. What can we do? They cancel. Okay, they cancel. 1 plus sine is the same as sine plus 1. So those cancel. So we've got sine of theta in the numerator. We've got cosine squared in the denominator. How can we move cosine to the numerator? Its reciprocal is secant. Ta-da! Look at that. That one, I'll give it to you. That one's difficult. Okay, that one is a tough one. It is a tough one. Okay, but the moral of the story with this one is pretty much you're using every bit of algebra you've ever learned to work these out.
What's algebra?
Okay, let's look at this one. Let's look at this one. Which side of the equation do you think we should work on? The left side?
No, the right side.
Really, with this one, it doesn't matter. Okay, it really doesn't. We can do this one both ways. So I heard left side first, so let's try and manipulate the left side first. Okay, so I don't think that I really want to expand that 1 plus sine of theta squared because I'm going to have to write it twice and FOIL it out, and I don't really see how that's going to get me to the right side. Is there something that I can replace cosine squared with? What is cosine squared equal to? 1 minus sine squared? Cosine squared can be rewritten as 1 minus sine squared of theta. Now, anybody see anything there? What about the denominator? They're almost the same. We can't just take away the squared. Can we factor it in? Can we factor anything? Okay, so the top is a perfect square trinomial. Let's not FOIL it out, but let's write it like this. Okay. Now, is there anything we can do to rewrite that denominator? Do the same thing? Or how would we do the same thing? It's not exactly the same thing. 1 minus sine of theta times 1 plus the sine of theta. It's the difference. Well, I didn't hear anybody say factor. Well, that's not what I did on the top. I didn't factor on the top. I expanded on the top. And then we can cancel it out. Ta-da! And we're there. Okay, now let me show you how we could go the other way. Okay, because sometimes you can do that. Sometimes you can, you could work on either side. I mean, you can't work on both sides at the same time, but sometimes you can do either one. Okay, so here's what we would do if we started on the right side. The only thing mathematically that we can do is we can multiply by the conjugate of the denominator. Okay, so the conjugate of the denominator would be 1 plus the sine of theta. So from that, I'm just going to write down what I have on the right side here. From that, I've got 1 plus the sine of theta times 1 plus the sine of theta. That's just 1 plus the sine of theta squared. When we multiply that out, when we FOIL it out, 1 times 1 is 1. The outside gives us positive sign. The inside gives us negative sign, so they cancel. And then negative sign times positive sign is negative sign squared. And our Pythagorean identity says 1 minus sine squared. Whoops, I'm trying to think. I'm right. 1 minus sine squared is cosine squared. So, either way, either side, you can get it.
Will they
Do what?
Will they ever give you like a proof or they're not on
No. It will always be provable. It will always be true. It will not be a trick. Okay? All right, so